Hello people, this short video segment is to show you how to plot the force deflection curve in the finite element module of the 3DEXPERIENCE version 2022x. The reason I insist on the version here because this software is regularly updated, I think 4 or 5 times a year, and as they do that, they make certain changes. Now I know that this process is going to work for 2022, but next year, hopefully, there are no changes which affect this. The If you're an Abacus user, you have probably we can get this thing done in with some detective work because the software that's embedded in the fundamental software that's embedded in 3D Experience is the Abacus program. So if you are an Abacus user, then you have some idea of what to do. But if not, then it's very tough to get this thing done because it's not uh, well documented in the 3D Experience online documentation. Actually, it's not documented at all. Okay, so the problem that I'm going to be doing is a simple one: a block clamped at the end and subjected to a concentrated force here. Now, if I solve this thing as an elastic problem, the force deflection curve that you're going to get is going to be a straight line, and I don't want to do that. I want to do something a little bit more, you know, complicated. So instead of doing an elastic calculation, I will do that as a elastic fully plastic uh, calculations. Anyway, the message is shown here for you, and thanks to this gentleman here from Dassault System who guided me to get this thing done, going in the proper direction. Now, the material, as I said, is elastic, fully plastic. So elastic, I'm using the property of steel right there, 20 gigapascal, 200 gigapascal and zero point 0.3 for Poisson ratio, and I'm assuming that the yield strength is 100 megapascal. So this is the basically the stress versus plastic strain. So because it's fully plastic, it's going to be a horizontal line, and you can actually show this thing. There is no hardening here. You can show this thing by right-clicking and saying XY plot. But here is the way, this is hand-drawn, of course. So if you plot the stress versus strain, it's going to be stress, linear stress, and then flat for that yield strength. But because the information that goes in here is actually stress versus plastic strain, you have taken away the elastic portion of the strain, and you get a horizontal flat line at this height. Okay, and this is not drawn to scale. Now, uh, so the problem that you want to do is to find the deflection of the point A as a function of the applied load at the point A, and you get a curve like this. Okay. Now, in order to do that, first of all, you have to request some data because you want to plot them later on. So in the Simulate tab, you have to ask for the data that is being saved for post-processing later on. And once you run it, once you run the results work, finish basically and generate all the results, then you have to go to the plots tab and uh, recover two two curves. Now these are displacement of the point A versus time. Now remember, this is a dummy time because you're solving a static problem. And the concentrated force, not the reaction force, concentrated force at A versus time. And once you do that, then you can use this feature to combine them. These look familiar if you're Abacus user because there are corresponding things in Abacus. But okay, so let's go ahead and do that. We go to part design. So on that vertical plane, I will sketch a rectangle that's 200 by 100. Size of the block was 200 by 100. This was 200. Okay, and this thing is 100. Exit, and then pad it by 50 millimeter. Okay, so let me go ahead and create my material here. Uh, Create a material. I'm going to call it, today is February 22, 2022. Okay, and make sure that the simulation is checked. It is checked here, and say okay. I'm going to apply this. Well, actually, let's see now. Let's see. Not this one. Sorry. This is the one. This is the one that I just created. So simulation, structural, abacus multiphysics, mechanical, elasticity, elastic, and I said it's going to be 2e to the 11, correct? 2e to the 11, that's, yeah, 200 gigapascal. Poisson ratio is 0.3. Okay, and then we go to plasticity and use the numbers that I had. So that was 100 e to the 100 megapascal, right? 100 e to the 6 at plastic strain of 0. So basically that's my yield strength. And same thing, 1 e to the 8 at, at a plastic strain of 0.001. Now, if you want to see this, whether it worked or not, whether you input it correctly or not, you can right click and say exploit plot. It's a flat line at that height. We know that. So we say okay. Good. Now we're going to apply this. Right click, apply. I am going to minimize this, apply to that part, and we check, make sure everything is there. Yeah, good. Okay, so let me save this. Now we're going to go to our structural model creation for meshing and things like that. Structural model creation. Let it mesh automatically. The size 10 millimeter. Okay, there it is. Okay, now we are going to go to structural model creation. Sorry, not model creation, structural scenario creation. Let's use the finite element model that we just created. All right, get the green check mark here, very good. So for procedure, we go static step. Now, I don't want to leave the time step one, initial time increment one, and maximum time increment one, because it's going to do it in one step, and I want to get a force deflection curve at different levels of load. So I'm going to make this thing initial time increment of 0.01, and the biggest time increment is also 0.01. Basically, it's going to be 100 steps in between, and total time is 1 plus 100 steps in between. All right, because by default the large deformation, or let me see now, large strain is on. Yeah, we'll just leave it the way it is. Okay, good. So now we're going to go to restraint, clamp this end, and apply the concentrated force. Now, concentrated force, of course, is nothing that's physically realistic, but we don't want to check the accuracy here. What we want to do is how to create a force deflection curve. That's all. So minus 10,000 Newton downward, and say okay. Now, before you run this thing, we can run this thing, but the problem is that if you run it, we can't get the graph that we want. Notice that what we need to do, we have to go and ask for data. Okay, so you go to we are in procedures, click on the simulate, and just ask for additional data. So let's see now, we go here, we go to simulate, ask for additional data, output. So what we want is displacement, translation. Now we don't need the rotation translation. There is no rotation here because it's a solid element. And down here in the forces, make sure you ask for CF, concentrated force, not RF, because this is not a support. Okay, no constraint here, so we have to ask for concentrated force, and we're going to ask it at every increment for the whole model. That's the total waste, because all we want the information for that point. Now you can create probably you can create a group there or a set there, as Abacus calls it, and ask for information there. But I'm going to ask that every entire model at every increment, which is unnecessary. All right, now we're gonna run it. We're gonna run it. So we basically did this. After we run is where we have to go and extract some information. Okay, good. So let's check, do a model check. No problem. This one is I think scenario check or something like that. I mean, very often I skip these, which is a bad idea. But if there are any messages, at least if there are any problem, you should get them before you run it. So it's going to be quick. It's called scenario check. Simulation check status. Simulation check status. If there are any warnings, then you go and read it. If it's critical, you change it. Otherwise, sometimes you just live with it. Okay, it's going to be done. Done. And now we can run it. As I said, if you're an Abacus user, then with some detective work, you can basically work your way through it. It's not going to be easy, but it's possible. But if you're not an Abacus user, this stuff is not, you can't get it out of documentation. All right, so it should be done very quickly. See that? It's going very fast, although it asks for a lot of stuff. And yeah, don't think I'm going to be getting any errors either. Okay, so, okay, good. Now, let me close this. And notice that this is the initial step, but as you go further down, this is the von Mises stress, and you can see that. You can see that things begin to plasticize there. And this is the final load of 10,000 Newton. And by the way, it's this is von Mises stress, but if you go to, which incidentally doesn't go beyond the yield strength, because yield strength, assume it was 100 megapascal. So if you go to deflection, displacement, it's about 0.1 millimeters, 0.1 millimeters at the full 10,000 Newton. Okay, good. So now we're going to go try to do our force displacement thingy. So first of all, let me get the undeformed geometry here. Okay, good. All right. So now we're going to go to plots right there. And this icon, it says XY plot from the field. That is this. Okay. So you click on it, move this thing on the side so we can see what's going on. And move this thing here. Okay, what do we want here? We want, first of all, the support. The support is that point. Okay, so I'm going to select this point. Now notice that first of all, it doesn't look like exactly the point that it's not that corner, quite that corner. So if I click on this edit option, this is the point that it took, but I don't want this thing to be 198, 200. I did not really pick it. Okay, so now it moved to that corner. And what is it that I want? I want the displacement and full magnitude, the magnitude, or you can put any components that you want. I put down magnitude, that's fine. So actually, you know what, let's do the displacement in the direction 3. Or we can do magnitude. I'll leave it magnitude. And just let me just give this thing a name that I can recognize. XY field. So this is displacement. You can give it a name that you want. That's okay. And then if you say apply, it's going to give you the, the, the displacement versus dumbing time. Now, dumbing time is basically the load level, okay? However, what I want is force versus displacement. I don't want something like that. This is fine. I need it, and I created it, okay? All right, let's do another one. And for the other one, notice that as you do this, these graphs are generated here. See it right there. This is the one that I just generated. Let's do another one. This time is going to be not displacement, but at the CF. Remember I asked for CF, reaction force. Actually, I'm sorry, let me put it back. This is what I want. CF is down here. That was the template. Oh, no, never mind. Concentrated force. If I had not requested those, these would not have happened. And then once again, that's the same point. Okay, if you want some other point, you can do it, but the same point. Apply, and this is the force. It doesn't surprise me because I'm applying 10,000 Newton, and it's going to uniformly increase it until it reaches the end. So say close. I'm done with this. Notice that I have created two graphs. This was displacement. This was the concentrated force. Now, if you look at my transparency, you're going to go to XY plot from expression. Okay, so let's go back here. You click on this XY plot from expression. Select this thing. See that? This f of x. See this? F of x. And select combine right there. Combine. Notice that what happens is that it takes two curves, or yeah, two curves, and combines them, uh, basically eliminating time. So here is the see combine in parentheses. So you select this. That's going to be the first one. It's going to be force. That's going to be displacement. And the second one, right there. You see this? And then apply. And there we are. So notice that the horizontal axis is displacement in millimeter and force in Newton. Now, uh, one option would have been to take those force versus time and displacement versus time and create and export them as Excel files and do all kinds of weird post-processing yourself, but it's not necessary. It's right there. So if I close this and close that, everything is here. And if I save this thing, come back tomorrow and change the load, let's actually try it. Let's actually try to change the load. Okay, so let's go here and change the load, make it smaller, 1,000, and then look at, repeat the same problem, run the same problem. So here under load, instead of 10,000, we make this thing 1,000. Say okay. Now I'm not going to check all of these. Everything has already been done. Data has been requested, graphs have been generated. You can see those things are already here. You can see that. So all I have to do is to run it. I'm not going to bother with these because I know that there are no issues. So I'm just going to run it. Okay. Now this is 10 times smaller load, therefore it's not going to put it that much in the plastic regime as before. So that curve probably is not going to have as much curvature. Obviously, if it's completely elastic, it's going to go straight line as a straight line as a straight line. This way you can plot anything versus anything else. one node versus another node. Okay, so this combine is the key feature, because if you don't know how to, if you don't know that there is this thing combine, pretty much hopeless. And combine is inherited from stuff in the Abacus CAE software. That's what's buried in here. Okay, good, good. So let's close this. Let me close out. Now, if you go here, if you go to this expression, see that? If you go to this expression, double click on it, and then if you say apply, there, it doesn't even go into the plastic range. Okay, basically force displacement is linear. All right, that's pretty much it. Good luck.